Thanks. I will begin with a word of prayer here. Heavenly Father, we thank you for this day. And Lord, I thank you for this class and just pray that you just guide our steps today, Lord. In your name I pray. Amen. So, I think I should give you some more examples. What we're going to try to do today is look at, ways to solve first-order differential equations, and also some various applications where they arise. All right. But my first example is just a math example, which does have another sort of aspect to it. It's the I guess maybe the first problem I've worked in here where the answer involves an integral. So sometimes you might say that this is finding an integral solution, but we've got dy dt minus ry equals to g. So here, r is a constant, right? And then g is some, let's say, continuous function of t. I mean, you could weaken that. G could just be piecewise continuous. What I'm about to do would still make sense, all right? But let's just suppose it's continuous just to be boring. All right, so what kind of differential equation is this? Can you recognize what this is? Is it separable? Is it exact? I haven't really defined separable carefully. I mean, separable just means separation of variables works on it. It might be separable. It's not, I don't know. I mean, that's kind of a pain, right? If you tried to separate y from t, I mean, there's like a t inside g, right? So think about what would happen. If you added ry to the other side, then you have like g plus ry. Can you factor g plus ry? Can you like separate g plus ry into like some function 1 of t and times some function 2 of y? Because that's the kind of thing you'd need to do separation of variables here, right? I don't think that's possible for an arbitrary function g there, right? So probably separation of variables isn't the way to go here for arbitrary g. And in fact, if you should recognize that this is what kind of differential equation is this? We talked about it last time.
Integration factor.
Integration factor method, right? This is a linear first order ODE, right? With what? P equals to minus r, and for what it's worth, q equals to g. In fact, it's already in standard form, right? So we can do. So let's try the integrating factor method. So step 1, calculate the integrating factor. What do we got? I is the exponential of the integral of minus r dt here. You know, if your differential equation has independent variable t, you integrate over t. If your differential equation had independent variable x, you do the integral in x. Like, you know, what integral you do to construct the integrating factor depends on your independent variable, right? Which is the variable with which the derivatives are being taken with respect to here. Like this is t. All right, so that's why I have integral t. Anyway, this is an integral you can all do. This is just exponential of minus r t, yeah? Because the integral of dt is just t, so there you go. E to the minus rt is the integrating factor here, apparently. So multiply. Multiply by I, we get e to the minus rt dy dt minus r e to the minus rt y equals to g e to the minus rt, right? And what did I say? If we calculate the integrating factor correctly, we should see the reverse product rule in the next step. right? In other words, I should be able to regroup these terms and see them as the total derivative of a single thing, right? So there's apparently y, right? And what's this right here? That's nothing more than the derivative of that, right? The derivative of e to the minus rt is minus r e to the minus rt. So this is the derivative of e to the minus rt times y. That's not an accident. That's the integrating factor times y. That's what we should see. But you should think through it to make sure you calculated the integrating factor right. Now that total derivative is equal to g e to the minus rt, right? So integrate both sides. That says that e to the minus rt is equal to the integral of g e to the minus rt dt. And if I want to think about that integral as a specific antiderivative, I probably should add a constant, right? If you want to think about this integral as being a specific fixed antiderivative, I mean, that's what I'm doing anyway. I'm going to add a constant just to, I'm thinking of that integral as not having a constant in it. Well, I have to add a constant when I integrate, And I've lost something. Yes. Y, which I'm going to write over here because I had space for it. And then multiply both sides by what? Y is equal to c1 e to the rt plus e to the rt times the integral of g e to the minus rt dt. There you go. That is the general solution to this problem, up to an integral. An integral you cannot do unless you know what g is, right? And in principle, even if you know what g is, you might not actually be able to hack the integral. But fortunately, there are robust numerical methods for dealing with integrals. So finding an integral formula for something is useful, even if you can't do the integral, because numerical methods are really good for integrals. Of course, there are also numerical methods for solving differential equations directly, which is the sort of thing you will learn in Math 352, right? Advertisement. All right. Anyway, any questions? Yep. Okay. So a special case of this would be what? Lots of special cases, but here's a special case. If we look at g equal to, say, 1, I don't know. Well, let's say a constant. I don't know. 42. So we'd be solving, something like dy dt minus ry equals to 42. Then allegedly the solution is y equals to c1 e to the rt plus e to the rt integral of 42 e to the minus rt dt. What's that do? What's the integral of 42 e to the minus rt dt? That's minus 1 over r, right? Times 42 e to the minus rt. And then this and that cancel, and we just get what? Looks like 42 over r, yeah? Another interesting case, let's be more specific. Let's consider, just to make this a little bit less abstract, r equals to 1 and g equals to e to the t. So we'd be solving dy dt minus y equals to e to the t. Then this general solution I just worked out would suggest what? Y equals c1 e to the t plus e to the t times the integral of e to the t dt. Just a second, guys. I'm sorry. I'm supposed to put an e to the, oh yeah, e to the minus t, right? If I could follow my own work, e to the minus t dt. What happens with that then? E to the minus t and e to the t cancel out. We have the integral of dt. What's the integral of dt? Just t. So there we go. Y equals to c1 e to the t plus t t to the t. This calculation is relevant to about a week or two from now. We'll say things like, you have to put a t when the root is repeated. This gives you an explicit calculation showing you the appearance of the t in the repeated root case. That makes no sense to you right now, but your future self might appreciate this comment, okay? Like imagine yourself 3 weeks in the future as you're struggling to understand, wait a minute, 2 weeks, 3 weeks, I don't know, a certain number of weeks in the future. This comment is helpful. All right, enough about this. Could any of these problems, these special cases, have been solved with like separation of variables? I mean, I think so. Let me just make it a little bit more, slightly separate example. If we were going to solve dy dx minus y equal to, 10, we could use the technique, the general solution I just found, to solve that problem, right? But this problem could also be solved as follows. See, this would say dy dx is equal to y plus 10, right? So then this gives us dy over y plus 10 is equal to dx. See, in that case, this problem is clearly separable, right? And so you can use separation of variables, integrate both sides. What do we get? The natural log, the absolute value of y plus 10 equals to x plus some constant. Now, if we just wanted an implicit general solution, great, we're done, right? We could say, okay, well, good for us. There's our implicit general solution. I guess I usually say it's the implicit general solution, but to be completely honest with you, I'm missing one case. What's the other solution that's not included in the boxed equation? Y equals minus 10, right? Y is just identically minus 10. That function, the constant minus 10 function, solves the differential equation but escapes our separation of variables, because that's where we divided by 0. That's our extraneous solution here. I mean, and that is a possible solution. If that's the differential equation that your model allows, then if you have your dependent variable equal to minus 10, guess what? That's like a steady state solution. It just stays there. It just lies there at minus 10. It doesn't move, Now, if I want to solve for y, this gives me the absolute value of y plus 10 is equal to e to the x plus c, right? Which I could simplify as e to the c times e to the x using laws of exponents. That gives me y plus 10 is plus or minus e to the power c, e to the x. Therefore, y is minus 10 plus k e to the x. And it's a kind of funny thing, but in calculating the explicit solution as I just did, if you look at the definition of k here, right, what's k equal to? K is equal to plus or minus e to the c in this derivation. Is e to the c is positive, right? Exponentials are not 0. So technically speaking, following the derivation, it seems like k shouldn't be 0, right? But what does k equal to 0 actually give us? That gives us the extraneous solution. It's kind of a quirk of the mathematics. A lot of times when you find the explicit solution, the same lack of attention to detail in the algebra that lost a solution will actually add it back in, right? So like the inattention I'm talking about is just labeling this thing k without noticing that, hey, strictly speaking, it couldn't be 0. So, I mean, logically, the fact that k could be equal to 0 is added in because this is just a separate case. And it's just so nice that that one formula for the explicit solution contains all possibilities. All right. The moral of the story I'm telling you is just that every fussy bit of algebra that you learned before is still relevant here because we're doing algebra, because we're doing calculus. And to do calculus, you have to do algebra, right? Let's try this problem here. Let's find solutions of 2xy squared dx plus 2x squared y minus sine of y dy. Right. Now, side note, how is a different way this problem could have been presented? Well, first of all, there's a 0 missing, right? What's an alternative way this problem could have been presented? How else could I have given this problem to you? I could have given it to you in the following format. I could have said solve dy dx equal to, 2x y squared well, sorry, having a moment of, okay, yeah, divided by sine y. I have to trying to think in my head, which is a dangerous thing some days. 2x squared. Like you think outside your head. Well, yeah, that also seems wrong. I don't know. Yeah. The reason I don't need to flip it is because when you multiply this over to here and that over to there, then you have to move the dy term to the other side, which introduces a minus. So, yeah. So that's the same differential equation. Well, that's not quite honest, is it? I mean, ignoring the denominator being 0, it's the same differential equation, all right? So, anyway, sometimes I would present the problem in this way and say solve it. Now, if you saw this problem and I said solve it, you would look at it and you would go, oh, no. Like you should immediately give up on separation of variables for this, right? Can you factor this thing into something like some function of x times some other function of y? See, that's what you would need to do separation of variables, right? You have to be able to separate before you can separate and integrate. I can't do it for that because there's that sign of y is just hopeless. There's no way to factor a y out of that, right? And it's not linear. Look at that y squared. Y squared says nonlinear. So by process of elimination, this is an exact equation problem. Because you got three methods in here, right? Or it's a substitution. But if it's a substitution problem where I didn't tell you to make the substitution, you have somehow offended me as a class, right? Because traditionally I will tell you the substitution if it's a substitution problem because those are kind of beastly for introductory students. All right, so I think it's exact. Let's see if it actually is exact though, right? We can do the closed test. So here's my my m, here's my n. What's partial m, partial y? Looks like we got 4xy. What's partial n, partial x? Looks like we got 4xy. Yay. Right, so meets the closed condition on the plane, which is simply connected, therefore it's exact, which means we can find a potential. We can find a level function, which the level curves are going to be the solutions. Yeah, question?
Outside-ish. Just as so you said the four methods were separation of variables, exact, substitution, and what's the other one?
Integrating factor technique, linear. So a linear ODE. Now linear ODE has to have the form dy dx plus py equals to q. The p and q can be all kinds of weird functions of x. That's fine. But the point is that the dy dx and the y are not squared. They appear in the linear sense. That's a linear ODE. And so for that kind of thing, we have the integrating factor method. This is not that, though, because it's got a y squared. So we're up a creek as far as that's concerned. So it has to be exact, and which means we're trying to solve, right? We're looking for partial f partial x equal to 2xy squared, and we're looking for partial f partial y equal to 2x squared y minus sine of y, right? So we're trying to solve both of these partial differential equations at the same time, actually, to find our solution. You're like, wait a minute, I thought you said we weren't covering partial differential equations till the end of the course. What are you talking about? I'm sorry, it's not my fault. You were already solving partial differential equations in this sense in Calculus 3, right? Or if you took my physics, I had you do this. I don't think any of you guys had my physics, did you? No. It's lost to history. But I used to teach like a little bit of Calculus 3 in Physics 231 here, just for, for giggles. Actually, no, because Physics 231 without Calculus 3 is kind of dumb. All right, so f of x comma y apparently is equal to x squared y squared plus some constant. And here we're integrating with respect to x holding y fixed. So the constant is possibly a function of y, right? So here this arrow is integrating with respect to x holding y fixed. Now, I have a shorthand notation for that idea, and here's my shorthand notation. I think you can appreciate it. If I want to say I'm going to take the integral with respect to y holding x fixed, I just say it's this kind of integral. Ah, come on. Y. It's like an integral over partial y in some sense. I'm treating y as a variable, but I'm holding x like a constant in this integration process. So it's an anti-differentiation. It's the antiderivative version of partial y differentiation. Anyway, so f of x comma y equal to, well, that again gives me x squared y squared, right? And then the integral of that is cosine y, right? And then because it's an integration holding x fixed, I have plus c2, which is a function of x. And then what you can do is you just compare these two, right? And we've already checked the closed condition, so we know that f exists. It's just a matter of calculating it, right? And what do we get? F of xy equal to x squared y squared plus cosine y. That's my level function. Now, is that the answer? If you say that that's the answer, I take off about 30% credit, because it's not the answer. It's used to make the answer, but it's not the answer. What's the answer? We're looking for a solution. What's a solution? We can either write a solution as an implicit or an explicit solution. If it's an explicit solution, it's a graph. If it's an implicit solution, it's an equation whose locus, whose set of solutions is the solution, right? Set of x, y that solve it. So what's the solution? It's not that. It's that equal to a constant. That's the solution. Thus, by the theory we talked about. X squared y squared plus cosine of y equals to some constant. Now, if we wanted to find a specific solution through a given point, then we would need more data, right? Do you guys want to pick a point and see if we can find the solution through it? Let's do it. I will choose the y-coordinate. Let's suppose it's -3. Blank -3. So you guys find an x-coordinate. You want to use 0? 0 worries me slightly. It might work. Give me 1? All right. Now, this is going to be on which choices? See, which level curve is this point going to be on? You're like, how do you know that there exists a level curve which that point's on? I don't know that for certain, but I'm pretty sure it is. If I plug in x equals to 1 and y equals to -3, I get like 9, right? Plus cosine of minus 3, which is just cosine of 3. So this is on the c equals to 9 plus cosine of 3 curve. So in other words, x squared y squared plus cosine of y equals to 9 plus cosine of 3 is the, I mean, if I just wanted the implicit equation which fits that data point, I'm good. Now, I want more than that, though. Let's find the explicit solution through that point. Find the explicit solution through that point. Explicit solution through 1 comma minus 3. What's that mean? Algebraically, that means oh. Well, you know, it's like, let me, I can want to find an explicit solution, but that doesn't mean I can actually do it, right? Like here is a good example of one that, can you solve for y? Can you solve that for y? Not through closed form means, right? I could appeal to a theorem of advanced calculus which says that, if I check a certain condition on that, I can solve for y as a function of x, but that doesn't actually mean I can actually find the formula for it. All right? So here, that would not be a reasonable question to ask you on a test, like to explicitly find the explicit solution. To go further on that is a discussion of advanced calculus, so I'm going to stop there. All right, so some different methods. I hope that helps make a little bit more sense of the different things we're doing: separation of variables, integrating factor method, exact equations, right? I should warn you, if you don't check the closed condition, right, and you just go ahead and do both of these partial integrations, you can always do these partial integrations, almost always, right? You can always do them. But if you try to do them to a problem which is not exact, what's going to happen is you're going to get things which are just inconsistent. It's going to force your function of y to be a function of x and vice versa. It will lead to a contradiction if you try to do it on an exact equation. So another algorithm is to solve the first one and then to plug the first one into the second one and then and to deal with that. That's the other algorithm, which is safe. This algorithm is dangerous if you don't start by checking the closed condition. Checking the closed condition means I can find the f. If I don't check the closed condition, then this algorithm won't quite work for you. You need to actually do this step and then plug it into there, which you'll see me do in the notes some places. All right, so let's look at some applications. Let's see here. I'll start with a somewhat, well, actually, you know what, tell you what, I'm going to let you choose your own adventure. Student's choice. Which would you rather see? An application or an example of substitution? Example of what? Substitution. Okay. All right, let's, ooh, this one's, well, all right. So suppose you wanted to solve dy dx equal to x plus y minus 6 quantity squared. So in this case, the substitution, I mean, this is almost on the cusp of like, maybe I could assign this on a test reasonably and just let you figure it out for yourself, you know? Because the substitution just kind of screams at you what you should try. What would it be? The what? Yeah, the thing in the, exactly, x plus y minus 6. And so we need another letter for that. We're going to call it v. V is equal to x plus y minus 6. So if you do that, then at least with respect to that substitution, this is much nicer, right? That's v squared. But then the pesky thing is that dy dx is no longer what we want, right? We need to relate dy dx to dv dx. But that's not too bad, because once you make the substitution, you can differentiate that, and that will give you the relation between the rate of change of v, right, and the rate of change of y, which is 1 plus dy dx. So solve this for dy dx, what do we get? Dv dx minus 1. So I'll have, so this, in view of this, right, in view of star, using star, dy dx is dv dx minus 1. So once we make the substitution, hey, that's not bad. I think it's not bad. Not sure yet. What do you guys, how should we solve this new equation? What do you guys think? Thoughts? Stupid. Ooh. Yep. Nothing to see there. Nothing to see. All right, so dv dx is v squared plus 1. Wait a second. This is separable, right? Because you can just, this gives us dv over v squared plus 1 equals to dx. You guys are all entirely familiar and up to date with your calculus too, so you know instinctually that the integral of 1 over v squared plus 1 is inverse tangent of v. Good. All right. So we settled that. Good. Good, good, good. So when I put that on the test and or quiz, you won't be surprised by it. Glad to hear it. All right. So this implies that the inverse tangent of v is equal to x plus a constant, right? And then that's not the answer, right? You want to undo this, just like when we do u substitution, you don't leave your answer in terms of u. We don't leave our answer in terms of v, right? We want to go back to x and y in the end product here. But I'm going to do a little bit of algebra before I do that. That gives me v is equal to the tangent of x plus c, taking the tangent of both sides. But v is what? So we've got x plus y minus 6 is equal to the tangent of x plus c. So this gives us y is equal to 6 minus x plus the tangent of x plus c. And there you go. That's the solution to this thing. It's not too bad, is it? No. I'll do another one, which is known as a Bernoulli differential equation. It's a pretty good example. Y prime plus xy equals to xy cubed. All right. And I'm going to call this star. So for what it's worth, this is my example 2.4.5, which is on page 28. There's actually a text bubble right under that giving you more general advice about how to solve things like this. But I'm going to follow the notes here more or less. So the idea that the notes put forth is we should multiply by y. I think what I'm going to do is ignore my notes and just make a z equals 1 over y squared substitution. See what happens. All right, let's try. Um, maybe not. Just let me back up here for a second. Let me just try. Let me foolishly try to think through this as opposed to just copying stuff down from my notes for a second. If we divide this equation by y cubed, what happens? Oh, that's not it. Fine. I'm sorry, guys. I sometimes suffer from indecision. Let's follow my notes. I said z equals y to the minus 2 is helpful here. Let's see why. Okay, so what's that mean? That means that, well, among other things, it means that zy squared is equal to 1, right? So you could differentiate this. What's that tell you? It tells you dz dx, right? Times y squared plus 2yz dy dx is equal to 0, right? So we could try plugging that into star and see what happens, right? So what's this? This tells me that y prime is actually equal to y squared divided by 2yz. There's a minus because I had to move it to the other side, and then dz dx, yeah? Which you could write as z prime if you wanted, yeah? So let's just plug star star, if you don't mind calling it star star, star star. I will plug star star into star and see what happens. So I've got minus y squared over 2yz dz dx plus xy equals to xy cubed. My goal is to get rid of all the y's and just have z's and their derivatives. Then it's a differential equation in z and x. Hopefully I can solve it. So let's see here. I got a z. Oh, z is 1 over y squared. How does this, what is this actually? I mean, we can write it out, right? That's y squared over 2y. What was z equal to? Z was equal to 1 over y squared. So what's this simplify to? Yeah, negative, like you said, minus 1/2 y cubed over minus y cubed over 2. Yeah. So this is actually minus y cubed over 2 dz dx, right? Plus xy equals to xy cubed. So it seems like we should divide that by the, I mean, we basically take the, multiply by the reciprocal of the leading coefficient. What's that give us? It gives us dz dx plus what? Well, minus 2xy over y cubed equals to minus 2xy cubed over y cubed. So I multiplied by minus 2 over y cubed, right, to cancel out the leading coefficient of the dz dx. You see what happens? The y cubes are canceling on the right-hand side, which is wonderful. We just have a minus 2x over here. And what's this here? The y and the y cubed. We have actually 1 over y squared there, right? So that's nothing more than dz dx minus 2xz equals to minus 2x. Well, now we're in business. Now we've got a differential equation just with z and x, and we've gotten rid of the y. What's in my notes that my brain won't, I have some fear of going through the calculation in the notes at the moment. I don't know why. It's just me. But I'm pretty sure what's in the notes is I'm just trying to motivate why I made a z equals to minus z equals 1 over y squared substitution, right? Setting aside that motivational question, you can see that it worked, right? I mean, we've gotten to a differential equation that we can solve. How would you solve that then? What method do we use on this one? What's that? What technique? What's the integrating factor? Right? The p here is minus 2x, so the integrating factor is actually e to the minus x squared. Yeah? So if we multiply the differential equation at the bottom of the board by e to the minus x squared, what do we have? We've got e to the minus x squared dz dx minus 2x e to the minus x squared z equals to minus 2x e to the minus x squared. If I did this integrating factor calculation correctly, the reverse product rule should work. Does it work? Are we in business here? Is it happening? What we got here? That looks like a d dx of, I think it's e to the minus x squared and times z, right? Because the product rule would give me e to the minus x squared times d dz dx. And then like derivative of e to the minus x squared is minus 2x e to the minus x squared, right? Which is what I have right here, times z. So that, yeah, product rule. And that's equal to minus 2x e to the minus x squared. And then we integrate both sides, yeah? So e to the minus x squared z is equal to the integral of minus 2x e to the minus x squared dx, which if you tilt your head and squint, you can see is what? What's that? Yeah, it's again e to the minus, yeah, exactly. E to the minus x squared, plus a constant, right? And so we can solve. We get z, right, equals to, apparently, 1 plus c1 e to the x squared. Multiplying the equation by e to the x squared, we get that. But what is z? Right, so apparently 1 over y squared is equal to 1 plus c1 e to the x squared, which then tells me that y is plus or minus 1 over the square root of 1 plus c1 e to the x squared. And of course, I could choose a specific plus or minus if I was given an initial condition, right, with a y being either above or below the x-axis. There's probably also an extraneous solution, right, a special solution. Can you see it now? What about y equals to 0? Y equals to 0 is also a solution to that problem, which is not even in that solution set, right? It's extraneous, yeah. So a substitution sometimes is married together with one of our other techniques, right? There are other techniques of substitution. I have one in the notes where I start out in Cartesian coordinates, and then like by converting to polar coordinates, it actually simplifies. That's another kind of substitution. There's probably a dozen different popular substitutions. Again, if it's a substitution problem, I will suggest the substitution in the test. Now, if it's a quiz, I might let you look for it, right? Because quiz is homework, so you have resources, so forth. But all right. I'll do one more problem here, and then I'll get on to the applications. So of course we can solve, first order problems using these techniques, but sometimes we can also solve a second order problem using an appropriate substitution. So here's an example of such a problem. I want to solve d squared y dt squared plus y equals to 0. All right. So I'm going to make a substitution of velocity. I'm going to say, okay, so I'm going to let v equals to dy dt. I'm going to try to make that a substitution, use that substitution. All right. Then what I'm going to notice is that, well, d squared y dt squared is actually what? That's equal to dv dt, right? In other words, the acceleration is the derivative of the velocity with respect to time. You know this. But what maybe you haven't thought about is you could rewrite that as dy dt dv dy. So what I'm doing here is the kind of sneaky thing. I'm saying, suppose we trade our velocity, which is a function of time, for instead velocity as a function of position. Right? Then the chain rule relating velocity as a function of time to velocity as a function of position is exactly this. So I just see the dy like, but this is v dv dy, which I love saying. So in other words, the acceleration is v dv dy. And so what do we have? We've got, going back to star reads v dv dy plus y equals to 0. How would you solve that problem? What kind of differential equation is that? What is it? Separable? Ah. Yeah, you could do that. Okay, fine. All right. I mean, you're not wrong. I just think I think in terms of exact equations, But you're right. I'll do it your way. Separate, integrate. And so we're going to have 1/2 v squared equals to minus 1/2 y squared plus some constant, right? Or let's see here. We could rewrite that as the velocity squared is equal to what, like some constant, some other constant. I'll put a bar on the original constant there. Some other constant minus y squared, right? But what is v squared? Remember, this is dy dt squared, right? Going unsubstituting, yeah? So take the square root of that. What do we get? We get dy dt is what? Plus or minus the square root of c minus y squared, yeah? Now, do you still have the courage to separate and integrate a second time? What do you think? Aw. You should stick with it. We can separate. So we just got to do these integrals, right? Tell you what, I'll do the right-hand side. You do the left-hand side. Let me call that C tilde, or C2 there. Now, the other side, of course, is a trig substitution, yeah? So if instead of C, if you allow me this sleight of hand to trade my c for a c squared, it makes it easier for me to write the solution. If you think about it, there's no loss of generality, because in order to have v squared equals to this, that's got to be a positive constant, which means you can write it as the square of another real constant. Otherwise, you'd have something negative equal to something non-negative, which would be troubling. So I can just as well write that as c squared. Think about it. And that's convenient for me, because then I can do this integral. I think it's the inverse sine of y over c, perhaps? What happens when you differentiate inverse sine of y over c? You get, let me think about the derivative of this right quick. That gives me 1 over the square root of 1 minus y squared over c squared, right? Times the derivative of that with respect to y, which would give me 1 over c. When you multiply that 1 over c into the square root, you get back to that. We have a winner. So that's the antiderivative of that integral. It's inverse sine of y over c. And that equals to plus or minus t plus c2. And now we can solve for y. What do we get? Y over c is equal to sine of plus or minus t plus c2. In other words, y is equal to c times the sine of plus or minus t plus c2. If you search your heart, you realize that you can just rewrite that as just as well as y is equal to a times the sine of t plus some phase angle. I mean, for different choices of plus and minus in the initial thing, it just corresponds to different choices of amplitude and phase for a sinusoid. Hey, that's kind of neat. You guys guessed this. Well, okay, you guessed cosine, right? But you might as well have guessed sine when I asked you the question, what's the solution to y prime prime plus y equals to 0, like last week, right? What's the difference here? We derived it, right? I mean, we just calculated it from integrations that we already know. So what's the better solution? Guessing that sine is the solution to that, or deriving it? Yeah, I mean, guessing, it depends on what you're after, right? I mean, guessing is definitely faster, so it depends on what you're interested in, right? If you're interested in, like, certain questions, what we just did is better. If you're just after the answer, then guessing is just fine, yeah. Okay. So, applications. One interesting application is the problem of orthogonal trajectories. What's an orthogonal trajectory? So you're given set of curves. All right, so these will solve, let's say, dy dx equals to, I don't know, f, for the sake of discussion, right? Then if you want to find the set of orthogonal trajectories that would look like these, I mean, I'm trying to say that they meet at right angles, right? What should these solve? Solutions to dy dx equal to what? What's the relation between the slope of the black curves and the slope of the blue curves? How are their slopes related? What's that? What do you say? Inverse? We're close. What's that? If I have the line with slope 3, what's the perpendicular line slope? Minus 1/3, right? We want the negative reciprocal. So we just put minus 1 over f. Solving this differential equation will give me those orthogonal trajectories. All right? Now, this same idea in terms of the Pfaffian forms, if we had, I'll use the color coding. If the black curves if they were solving m dx plus n dy equals to 0, right? Then to find the orthogonal trajectories in the Pfaffian form notation, you would want to solve instead, I mean, you got choices, but here's one, minus n dx plus m dy equals to 0. This would have the orthogonal trajectories to star. For an example, let's see here. Let's consider x squared plus y squared equals to r squared, right? Find orthogonal trajectories to given family of curves. Right. Now, I actually think you could solve this problem without differential equations, right? We should all know the answer to this without differential equations. We should know the answer to this as soon as we understand what orthogonal means, because we got circles concentric to the origin, right? What are the orthogonal trajectories to this? Our answer, we should anticipate, we should get what? These guys, right? Just the concentric line, lines from the origin, like that, right? That's what we should be finding those as our solution here, if we understand our method correctly, right? So what's the differential equation that solves? Well, I think the nicest way to do it is use the Pfaffian form personally. I mean, this says that 2x dx plus 2y dy is equal to 0, right? That differential equation in Pfaffian form has circles as its solution set. So I need to change it a bit by putting the minus in front and the 2y there, dx, and then plus 2x dy equals to 0. Solve the red equation. That should give me the orthogonal trajectories. So how do you guys want to solve the red differential equation? Yeah, I think separation, not a bad choice at all. So we got 2y dx equal to 2x dy. 2's canceling. And so we got dx over x equals to dy over y, apparently. Integrate log absolute value of x equal to log absolute value of y plus some constant. I regret putting the constant on that side. I'm going to put it on the other side. Hey. This is a freedom we have, yeah? And so then exponentiate both sides. We get the absolute value of y is equal to e to the c plus the natural log of the absolute value of x, also known as e to the c, e to the natural log of the absolute value of x, also known as e to the c times the absolute value of x. So consequently, y is plus or minus e to the c times x. Or you could leave an absolute value there. I mean, it's up to you. But so cleaning it up a bit, I think what we have is y equals mx, yeah? Now, because I've decided to present my solution as a graph of a function, right, it would appear that we're missing something, right? Like, it would appear you're missing the orthogonal trajectory, which is a vertical line, right?